Welcome to Grandpa's Late Nights. Come in, come in. Settle yourself down wherever you are. Pull the blanket up a little higher if there's a chill, and let your shoulders drop away from your ears. There's no hurry tonight. There's never any hurry here. The kettle's already gone cold on the stove, and that's all right, because you don't need anything but a soft place to lie still and a quiet voice to follow, and I can be that for you. So go ahead. Find the spot where your head sinks into the pillow just right. And before we begin, I always like to ask, where in the world are you tonight? What corner of the night did you carry yourself off to? Some of you are tucked into a real bed with the rain ticking on the window. Some of you are on a couch with one foot hanging off the edge. Some of you are on a long train or a long drive, somewhere between one place and another, and that in-between feeling is its own kind of cozy. Wherever you are, whatever the hour reads on whatever little glowing clock is near you, I'm glad you came back. Tell me down below where you're listening from if you've got the energy for it. I do love reading them. It's like getting postcards from all the dark corners of the world at once. And listen, if you enjoy these slow nights, these little wanders through big ideas, it does help this sleepy little channel an awful lot if you tap that like and subscribe. I know, an old man asking for buttons. But I'm a small creator, kiddo, just a porch light and a microphone, and folks like you who stick around are the whole reason the light stays on. So if you've got a free thumb before you drift off, that's all it takes. And to those of you who already subscribed, thank you. Truly. You're the regulars on the front step, and I never forget a face. Now here's my one promise to you, and it's the same promise every night. You don't have to follow all of this, you really don't. I'm going to walk us through something tonight that took the smartest people who ever lived 100 years to puzzle out, and I'd be a liar if I told you I expect you to hold on to every thread of it. That's not what this is for. This is for drifting. If you fall asleep before I'm halfway through, that is exactly what's supposed to happen, and you should feel good about it, not guilty. The ideas will still be here in the morning. They've waited around for 14 billion years already, so they can certainly wait for you. I'll try not to make this one so interesting it keeps you awake, but if it does, well, at least you'll have learned a thing or two on your way down. That's a fair trade, I think. And what a thing we're going to drift through tonight. We're going to talk about the very first instant of everything. Not the first year, not the first second, the first sliver of a moment, so short there isn't really a good word for how short it was. And I'm going to tell you that in that one impossible flicker, the whole universe more or less decided its own future, where every galaxy would eventually pile up, how the whole thing would be shaped, even how it all ends billions and billions of years from now, all of it more or less written down in an instant. And then I'm going to tell you the strangest part of all, that the universe left behind a single fingerprint when it did this. One mark, one signature, hidden in the oldest light there is. And we have been hunting that fingerprint for years now, and we still, to this very night, with you lying there in the dark, we still haven't found it. We thought we found it once. Oh, we did. Let me set this down softly, like a coal I'm placing in the stove, because we'll come back to warm our hands on it later. There was a night, back in 2014, when a small group of scientists were so sure they'd caught the fingerprint at last that they got in a car and drove across town to surprise one of the men who'd dreamed the whole idea up in the first place. A fellow named Andrei Linde. They knocked on his door with a bottle of champagne and a camera running, and they told him, right there on his own front step, that they'd finally proven how the universe began. And he stood there, this gentle, brilliant old man, and his eyes filled up. And his wife came to the door. And the whole world later watched that little video and felt their own throats go tight. The most beautiful idea confirmed at last. But they were wrong, kiddo. That's the thing I want you to carry into the dark with you. They were wrong. The thing they thought was a message from the birth of the cosmos turned out to be nothing but dust. Ordinary dust, floating in our own galaxy. We'll get to all of that slowly, gently, every twist of it. But hold that little ache in your chest for now. A team of people wept for joy, and then the dust took it back. We'll come round to why and what it means, and who's out there right now building a machine to try again. No rush at all, we've got all night. So, let's begin the way you'd begin any good story. Let's go back, way back, to the part where everyone thought things were already settled, because that's where the surprise lives. In the moment, people felt sure. There was a time, not so very long ago in the great scheme of things, when scientists looked out at the universe and felt they had the broad strokes, more or less figured. The big idea, the one you've probably heard 100 times, is that the whole universe started out unimaginably small and unimaginably hot, and it's been expanding and cooling ever since. People call it the Big Bang. And here's a funny little thing about that name, just a bit of warmth to tuck into the story. The name Big Bang was actually coined by a man who didn't even believe in it. A fellow named Fred Hoyle, back in 1949, said it on the radio, and a lot of folks say he meant it as a bit of a jab, a way of poking fun at the whole notion. Hoyle himself later said he wasn't being mean about it, so we'll leave that argument to the historians and just enjoy that the most famous name in all of cosmology may have started life as a tease. Names are funny that way. They stick whether you meant them to or not. But here's where it gets interesting. The plain old Big Bang picture, the simple one, it worked beautifully for a great many things. And yet, when the careful people sat down and looked at the universe in fine detail, they found themselves staring at a few quiet little problems. Not loud problems, not the kind that knocked the whole house down. More like a draft you can't find the source of. You know the feeling. Everything seems fine, the doors are shut, and yet there's this cool ribbon of air on your ankle, and you can't for the life of you figure out where it's coming from. That was the state of things. A few cool drafts in a house everyone assumed was sealed up tight, and the strangest draft of all was this. When astronomers looked out at the sky in every direction, and I mean truly every direction, this way and the exact opposite way, they found that the temperature of the universe out there was the same. Not roughly the same. Astonishingly, almost perfectly the same. The deep background warmth of space measured out to be the same to about 1 part in 100,000, no matter which way you pointed. Now you might think, well, of course it is. Why wouldn't it be? But sit with it a moment, the way you'd sit with a riddle a grandchild brings you. Imagine you've got 2 cups of tea on opposite ends of a very long table. One you poured an hour ago, one you just poured. There's no earthly reason they'd be the exact same temperature, is there? Things only even out in temperature if they've had a chance to touch, to mix, to share their warmth. A hot thing and a cold thing left in a room together will slowly meet in the middle, but they have to be in the room together. They have to have had time to find each other. And here was the trouble. The 2 opposite edges of the sky, the bits of the universe staring at each other across all of creation, they had never been in the room together. Not once. Not for a single instant. The universe simply wasn't old enough for light or heat or anything at all to have traveled from one of those far edges to the other. They had never touched. They had never traded so much as a whisper of warmth. And yet there they sat, the same temperature, like 2 cups of tea poured at opposite ends of a table, 1 billion miles long, somehow identical to the last degree. The scientists called this the horizon problem, and it troubled them, the way a thing that shouldn't be possible troubles you in the small hours. How can two strangers who have never met be wearing the exact same coat? That was one draft. There were others. There was the question of why the whole universe seemed to be balanced so perfectly flat. And I'll explain what a flat universe even means a little later, because it's a lovely, strange idea on its own. And there was a third puzzle, a stranger and more technical one, about certain heavy particles that the best theories of the day insisted should be scattered all through the cosmos, and yet nobody could find a single one of them anywhere. We'll come back to these in their own good time. For now, I just want you to feel the mood of it. The house of physics looked finished, painted, furnished, and still here and there a cold draft on the ankle that nobody could account for. And then, in the year 1980, a young physicist named Alan Guth was sitting and thinking about one of those very drafts. He wasn't even chasing the big questions about the temperature of the sky, not at first. He was wrestling with that third puzzle, the one about the missing heavy particles. The fancy name for them is magnetic monopoles, and you don't need to hold on to that. Just picture them as a kind of cosmic leftover, a relic the grandest theories of the time said the early universe absolutely must have churned out by the bucketful. Picture a bakery that by every recipe in the book should have produced 1,000 loaves, and you walk in and the shelves are bare, not a crumb. Where did all the bread go? That was Guth's puzzle. The theories baked 1,000 loaves of these heavy particles, and the universe's cupboard was empty. And the answer he stumbled into, the answer that would turn out to explain not just his missing loaves, but that whole cold draft of the same temperature sky, and the flatness, and more besides, was so strange and so beautiful that it took a while for even Guth himself to believe what he was looking at. He published the idea in 1981, having worked it out the year before, and the idea he set down on paper has a plain enough name. He called it inflation, cosmic inflation. And I want to tell you what it actually says, slowly, because it is one of the most staggering ideas a human mind has ever had, and it deserves to be unwrapped gently, like something fragile pulled out of tissue paper. Here's the heart of it. Inflation says that in the very, very beginning, not at the start of the first second, but at the start of a tiny, tiny, almost unspeakable sliver of the first second, the universe didn't just expand, it exploded outward in size in a way that makes the word explosion feel far too small and far too slow. For one brief flicker, space itself stretched. Not the things in space. Space itself, the very stage everything stands on, ballooning outward faster than anything you could ever picture. And then, just as suddenly, it stopped and settled into the calmer, slower expansion we still see today. Now I have to tell you when this happened and how long it lasted, and I want you to take a slow breath first, because the numbers here are the kind that make your mind go pleasantly soft at the edges. This whole episode of Mad Stretching, it took place somewhere around a time so early after the beginning that we write it as 10 to the minus 36 seconds, and it was all over and done with by around 10 to the minus 32 seconds. Now those are just symbols on a page. Let me try to lay them down in a way you can actually feel as you lie there. We say a trillionth of a second to mean something fantastically brief. Well, this happened in the first trillionth of a trillionth of a trillionth of a second. Read that as slowly as I'm saying it. A trillionth of a trillionth of a trillionth of one single second. The whole episode began and ended in a window so impossibly narrow that there is genuinely no everyday word for it, no human experience to compare it to. You could not blink fast enough, you could not think fast enough. The fastest thing you can imagine is a glacier next to it. It is, as near as makes no difference, the very first thing that ever happened. Before the universe had finished taking its first impossibly small breath, the whole drama of inflation had already come and gone. And in that flicker, and this is the part to drift on, in that flicker the universe grew, not a little, not double, not 1,000-fold. The standard telling has it that space stretched by a factor of at least 10 to the 26. The way the physicists put it, in their own quiet shorthand, is that it expanded by at least 60 e-folds. You don't need the arithmetic, you only need the picture. And the picture is this. Take a patch of the infant universe smaller than a single proton, T, and a proton, kiddo, is one of those tiny specks that live inside the heart of an atom, so small that millions upon millions of them could hide in the period at the end of a sentence. Take a patch smaller even than that, and in that one flicker of a flicker, stretch it until it is larger than a galaxy. Larger than the whole sweep of stars you see smeared across a clear night sky. A speck you couldn't dream of seeing, blown up bigger than 100 billion suns worth of room, in less time than it takes for the word instant to even begin. It's almost too much to hold, isn't it? That's all right. You're not meant to hold it. Just let it float past you like a slow, enormous cloud, the way you'd watch a hot air balloon drift over a field. There's no need to catch it, only to look up and feel small and warm and a little bit amazed, because that picture, that single proton-sized whisper of space blown up beyond the size of a galaxy, that simple, mad picture is what dissolves all those cold drafts at once. Think back to our 2 cups of tea at the ends of the impossibly long table, the same temperature though they'd never met. Well, inflation says they did meet. Once. Long ago, before the stretching, when the whole universe was a tiny, cozy thing, snug as can be, every part of it pressed warm against every other part. They sat together in a room small enough to share their heat, and they evened out, the way tea and air always do when they have the time, and then inflation came along and flung them apart, took that one little warm huddle and stretched it across all of creation, carrying the 2 cups off to opposite ends of a table that hadn't existed a moment before. So of course they're the same temperature now. They were friends once, in the warm. They just got blown impossibly far apart before they had a chance to say goodbye. That's the gift of the idea, you see. It takes a thing that looked impossible, strangers wearing the same coat, and quietly turns it into something tender. They weren't strangers, they were the same warm thing once, before the world grew up around them. And the same gentle trick handles Guth's missing loaves of bread, his vanished heavy particles. If the universe really did make a bakery's worth of those things in the very beginning, then inflation came along and stretched the whole bakery so unimaginably wide that the loaves got spread out thinner than thin, so far apart from one another, across the swollen new emptiness, that you could wander the entire observable universe for the rest of time and never expect to bump into a single one. They didn't vanish, they got diluted, like a single drop of ink stirred into an ocean. It's still in there somewhere, but good luck ever tasting it. The cupboard looks bare not because the bread was never baked, but because the kitchen suddenly became larger than everything. That's the part Guth worked out first, back in 1980, sitting with his draft and his missing particles. The astonishing thing is how much else came tumbling along behind it once he'd opened that door. He'd gone looking to sweep one small corner and found the broom had cleaned the whole house. The same temperature sky, the missing particles, the strange flatness. All of them soothed by the same single idea. One stretch, one flicker, and the cold drafts, every one of them, stilled. Now I'll be honest with you the way I always am, because you deserve honesty, even half asleep. Guth's first version of the idea had a wrinkle in it. It worked in spirit, but the details didn't quite hang together. When the great stretching tried to come to an end, it ended in a messy, uneven way that didn't match the smooth universe we actually live in. And so over the next couple of years, other clever people took his idea in their hands and smoothed it out. We'll get to who they were, and to the truly mind-bending thing they realized along the way. A thing about how every galaxy in the sky might really be nothing more than a tiny quantum hiccup that got too big to ever disappear. But that's a thread for a little later, when you may already be drifting, and that's fine. Let it wait for you. For now, just rest in the size of what we found. Just settle into it. A patch smaller than a proton, blown larger than a galaxy, in the first trillionth of a trillionth of a trillionth of a second. Everything you have ever seen, every star, every grain of sand, every face you've ever loved, descended from that one impossible flicker of stretching. The universe wrote the opening line of its whole long story before it had even finished being born. And almost nothing important, almost nothing at all, has been truly decided since. Stay with me or drift off if the driftings come. Either way, I'm right here. The dust and the fingerprint and the weeping man at his door are all still ahead of us, waiting patient in the dark. And we'll get to them. Slowly, softly, one mystery at a time. Now let me tell you about that weeping man, because his name is Andrei Linde, and he's one of the people who took Guth's wrinkled idea and pressed it smooth. Hold his name gently for now. We'll come back to his front door, and to the morning, a small group of scientists stood on his step with a bottle of champagne and news they believed would change everything. They were wrong. It was dust. But I'm getting ahead of myself, and we have all night, so let's not rush a single step of it. Let me take you back, though, to where this whole strange idea actually starts, not with Linde. With a younger man sitting at a desk in 1980 working on a problem that, at first glance, has nothing to do with the beginning of the universe at all. His name is Alan Guth, and the puzzle keeping him up wasn't how did everything begin? It was something far smaller and stranger. It was about a particle that should be everywhere, and simply isn't. Here's the thing about the physics of that time. The cleverest theories people had for how the forces of nature fit together, these grand, ambitious ideas with the grand, ambitious name of grand, unified theories, all quietly predicted something embarrassing. They said the early universe should have made a flood of heavy, lonely particles called magnetic monopoles. Now, you don't need to know exactly what a monopole is to feel the problem. Picture a magnet. Any magnet, the one on your fridge, the one in a child's toy. It has two ends, doesn't it? A north and a south. And no matter how many times you cut that magnet in half, you never get a piece with only one end. You always get a new little north and a new little south. Try as you might, you cannot saw a magnet down to a single, solitary pole. A magnetic monopole would be exactly that impossible thing. A north all by itself with no south anywhere. And the best theories of the day insisted the universe should be absolutely littered with them. Heavy, sluggish relics left over from the first instant, drifting through space in enormous numbers, so people went looking, and they found none, not one, not a single confirmed monopole in all the searching anywhere. That's a real problem, the kind that nags at a careful mind. Your theory predicts a swarm, and reality hands you an empty room. And that empty room, that absence, is the loose thread Alan Guth began to pull. Because what he realized, and this is the lovely turn, is that you don't necessarily need to explain where all the monopoles went. You just need a way to spread them so impossibly thin that the universe is enormous and the monopoles are so rare you'd be lucky to find one in a volume the size of everything we can see. And how do you spread something that thin? You stretch the space it lives in. You stretch it so violently, so suddenly, that whatever was packed tightly together gets flung impossibly far apart until a crowd becomes a scattering of single, distant specks. That's the seed of the idea. Take the early universe and for the very briefest instant make it grow, not steadily, not gently, but explosively, doubling and doubling and doubling again at a pace that beggars the imagination. Guth wrote it down in 1980, and the paper that carried it to the world came in 1981. He gave it a plain, almost humble name, inflation. Like a balloon, yes, but oh, so much more than a balloon, as you'll see. And here is where I want you to brace yourself gently, the way you might brace for a wave at the shore that you already know is coming. Because the numbers in this part of the story don't behave like the numbers we use to buy groceries or count the years. They're going to sound made up. They aren't. They're as honest as anything I'll tell you tonight. When did this great stretching happen? Not a second after the beginning, not a thousandth of a second, not a millionth. Inflation is thought to have begun and ended within the first trillionth of a trillionth of a trillionth of a second. Let that phrase just roll over you for a moment, because it's almost impossible to hold in the mind. A trillionth of a trillionth of a trillionth. We're talking about something like 10 to the minus 36 seconds at the start, all of it over and done by around 10 to the minus 32. Numbers so small that the words run out long before the zeros do. Think of it this way. You know how long a single second is, the space between one breath and the next. Now imagine slicing that second into a trillion pieces. You can't, of course, no clock could ever catch it. But imagine it anyway. Each of those slivers is already smaller than anything you'll ever experience. And then you take just one of those slivers and you cut it into a trillion pieces again. And then you take one of those and you do it one more time. And somewhere down in that unimaginable basement of time, smaller than small, briefer than brief, that's the entire stage on which inflation played out. The curtain rose and fell before the universe was anything you could name. The title of our little journey tonight mentions a trillionth of a second, and I'll be honest with you again, that's a kindness to the imagination, a rounding up. The truth is far more extreme than the title dares to say. It didn't take a trillionth of a second, it took a trillionth of a trillionth of a trillionth of one. And I tell you that not to make you dizzy, but because the real number is the more wondrous one. Why hide it? The strangeness is the gift. And in that flicker, that absurd, vanishing flicker of time, how much did the universe grow? Here's where my own breath catches every time. Physicists measure the stretching in something they call E-folds, which is just their tidy way of counting how many times over the universe doubled and doubled again. And inflation, in its standard telling, is thought to have run for at least 60 of these E-folds. 60. That doesn't sound like much, does it? 60 of anything. But this is the quiet trick of doubling, the same trick in the old story of the rice grains on the chessboard. 1 grain on the first square, 2 on the next, 4, 8. And by the end, the whole world's harvest can't pay the debt. 60 E-folds means the universe grew by a factor of something like 10, followed by 26 zeros. 10 to the 26th. In linear scale, in that one instant. So picture the patch of space that would become everything you can see, every galaxy your eyes or any telescope will ever reach. Before inflation, that whole patch was smaller than a single proton, smaller than the tiniest piece of the tiniest atom in your fingertip. And then, in less time than any number we have words for, it was stretched out larger than a galaxy. A speck you could never have found with any instrument ever built, blown up to a size you couldn't cross in 1 billion lifetimes. That's what inflation says. A proton-sized whisper of space taken in hand by some unimaginable force and pulled, not torn, not shattered, but smoothly, gently, impossibly stretched, until it became the wide and quiet sky you'd see if you stepped out onto the porch right now and looked up. and all those troublesome monopoles, the swarm that started this whole story, spread so thin across that suddenly enormous space that you'd be lucky to stumble on one in the entire visible universe. The empty room explained, not by erasing the crowd, but by making the room unthinkably vast. Rest there a moment with me, just rest in it. A force we still don't fully understand reached into the very first sliver of time and stretched the smallest thing into the largest thing, faster than fast, gentler than you'd ever guess from a word like explosion. There was no bang you'd recognize, no noise. Just space itself unfurling the way a sheet snaps open over a bed and then settles, slow and soft, down over everything. And somewhere in that unfurling, though Guth himself didn't yet see the whole of it, the seeds of every galaxy were already being sown. That's the thread I promised you, the one about the quantum hiccup, grown too large to vanish. We're nearly to it now. Andrei Linde is waiting just up ahead with his smoothed-out version of the idea, and, years later, with that knock at his door. But there's no hurry, none at all. Settle deeper. Let the proton and the galaxy and the 60 doublings drift together in the warm dark behind your eyes. So, let's talk about 3 problems. Not small ones, not the kind you scribble in a notebook and work out over a cup of tea before bed. These were the kinds of problems that could, if you stared at them long enough in the wrong mood, make a physicist wonder whether the whole picture of the early universe was simply wrong. Whether the Big Bang story, beautiful as it was, had some deep crack running through it that nobody had found a way to paper over. Inflation was going to paper over all 3 at once, but to feel how satisfying that is, really feel it, the way you feel a key turn smoothly in a lock. You have to sit with the problems first. You have to feel the itch before you scratch it. Let's start with the strangest one, the one that, honestly, should bother you more than it probably does because we've all grown up so accustomed to the universe looking the way it looks that we've forgotten how deeply, profoundly odd it is. Look up on a clear night, or imagine it, warm and dark wherever you are right now. The idea of a sky full of stars above you, even if there are walls and ceilings in the way. If you could see in microwave light, see the actual glow of the early universe instead of visible starlight, every direction you looked would be bathed in the same gentle warmth. The cosmic microwave background, the afterglow of the young universe about 380,000 years after the Big Bang, has a temperature of about 725 Kelvin. That's bitterly cold by any human standard, just a whisker above absolute zero. But the point isn't the number, the point is the sameness. In every direction to about 1 part in 100,000, the temperature is identical, east and west, north and south, toward any galaxy you care to name or any empty patch of sky between them. Same, same, same. And here is where you have to stop and ask yourself, why? Why would it be the same? Because if you pick a point of sky in one direction and a point in the exact opposite direction, let's say you're standing on the porch and looking east, and then you spin around and look west. Those 2 patches of sky are separated by something like 93 billion light years. Light has been traveling since the Big Bang, and it still hasn't crossed that distance, which means those 2 regions have never, in the entire history of the universe, been close enough to exchange so much as a single photon. They have never talked to each other. They have never nudged each other, never shared heat, never had any causal contact whatsoever. And yet they are the same temperature. In physics, if 2 things reach the same temperature, it means they've been in contact long enough to equalize, leave a hot cup of tea on a cold night, and eventually the tea and the air reach the same temperature. They exchange heat, they communicate, they settle. That process of reaching a common temperature is called thermal equilibrium, and it takes time. It requires contact. It requires that the 2 things were, at some point, close enough to interact. But those opposite patches of sky were never close, never at any point in standard Big Bang cosmology within reach of each other. And yet they are in thermal equilibrium, indistinguishable in temperature to 1 part in 100,000. This is what physicists call the horizon problem, and it is genuinely strange. It's a bit like waking up to find that two strangers on opposite sides of the planet, who have never met, never traveled, never spoken, who grew up in complete isolation from each other, have the exact same heartbeat, the exact same rhythm to within a tiny fraction of a percent. You would not shrug at that and say, well, coincidence. You would suspect some shared history you weren't told about. The horizon problem is that suspicion applied to the entire sky. Now, inflation. If the universe underwent that extraordinary exponential expansion and the 60 or more doublings, the proton to cosmos stretch, then everything in the observable universe today was, before inflation, packed into a region small enough to be in contact, small enough that a single photon could have crossed it, small enough that temperatures could equalize, that heat could spread and smooth, that the early universe could reach the same temperature everywhere before the expansion began. And then inflation took that small, already equalized patch and stretched it by at least a factor of 10 to the 26th in linear scale. Everything that grew to become the observable universe we can see today came from that single, already homogenized, already equilibrated region. The sameness isn't a coincidence, it's the memory of a time when everything was in contact, before space itself ran away with the distance. The horizon problem doesn't disappear when you invoke inflation, it dissolves. The question was never the answer to a mystery, it was proof that there wasn't a mystery to solve in the first place once you allowed that expansion. Take a slow breath with that. The same temperature in every direction. Not coincidence? Memory? The sky is remembering a time before space grew up and moved out. Now the second problem. This one is subtler, and it has to do with the shape of space itself. Not the shape of the things in space, the shape of space, the curvature of the geometry through which everything moves. And here I want to give you a picture because the abstract version is genuinely hard to hold. Imagine you're an ant living on the surface of a ball, a beach ball, say. You walk in what feels like a straight line, but after a while, if you keep going, you curve back around and arrive where you started because the surface you live on is curved. That's a positively curved space. Now imagine you're an ant living on a saddle, one of those horse saddle shapes curved up in one direction and down in another. Straight lines on that surface spread apart from each other as you go. That's negatively curved space, and between those two there's a perfectly flat geometry. Imagine living on an infinite flat table where straight lines stay parallel forever and the angles of a triangle add up to exactly 180 degrees. Our universe could, in principle, be any of those. Positively curved like the surface of a ball, negatively curved like a saddle, or flat. And crucially, in standard Big Bang cosmology without inflation, there is no reason, none, not even in principle, to expect that the universe would be flat. The equations allow all three options with roughly equal ease. In fact, they're worse than that. A precisely flat universe, according to the standard equations, is an unstable equilibrium, like balancing a pencil on its point. Any tiny deviation from perfect flatness in the early universe would have been amplified over time. A universe that was ever so slightly curved in the beginning would be dramatically, overwhelmingly curved today. To have the flat universe we observe now would require the initial conditions to have been fine-tuned to extraordinary precision, many dozens of decimal places, for reasons that standard Big Bang cosmology simply cannot explain. This is the flatness problem, and the data are very clear. When we measure the actual geometry of the universe, using the cosmic microwave background among other tools, space is flat. Not approximately flat. Flat to within about 0.5%. The curvature parameter, what cosmologists call omega sub k, is consistent with 0 to within the measurement precision we currently have. So the universe is balanced on that pencil point, impossibly flat, with no explanation in the standard picture for why. Inflation explains it. And the explanation is almost brutally simple. If you take any curved surface and stretch it by an enormous factor, inflate it, blow it up, expand it by 10 to the 26th times in linear scale, the local geometry becomes flat. Think of the surface of the Earth. It's curved, obviously, but when you're standing in a flat field, the local geometry looks and feels perfectly flat because the radius of curvature is so enormous compared to what you can see or walk across. Inflation did that to the universe. Whatever curvature the universe might have started with, inflation stretched it to such enormous scales that what we can observe, the entire observable universe, sits in a region so small compared to the total inflated space that it looks flat the way the local field looks flat. The pencil doesn't need to be balanced. It was never really a pencil, it's a curve so large that any reasonable piece of it looks flat. The flatness problem, like the horizon problem, doesn't need an answer. It needs to be unasked. And inflation does that. And then the third problem, the one that actually started the whole story, the one Alan Guth was chasing when he wrote down those equations in 1980 and realized, in what he later described as a spectacular realization, that he might have stumbled onto something important: grand unified theories. And this was the theoretical landscape of the late 1970s. Before Guth's paper, the particle physicists were building these beautiful frameworks that tried to unite the strong nuclear force and the electroweak force into a single description at very high energies. These theories made predictions, and one of their predictions was the existence of particles called magnetic monopoles. A magnetic monopole is, in a sense, half a magnet, a purely north pole or a purely south pole with no opposite end. Every magnet you've ever seen has both a north and a south. Break it in half, you get two smaller magnets, each with both poles. But grand unified theories predicted that in the hot, dense conditions of the early universe, particles should have been produced that are pure monopoles, and they should be extraordinarily massive and stable, essentially impossible to destroy. The problem is that the universe should be full of them. The early universe was hot enough, and the physics of grand unified theories requires monopoles to be created at a certain rate whenever the relevant symmetries break as the universe cools. Do the calculation and you get far more magnetic monopoles than there are ordinary particles. They should be the dominant stuff of the universe. They should be everywhere. And yet, no magnetic monopole has ever been detected, not one. In all the particle detectors and cosmic ray experiments ever built, not a single confirmed monopole. The universe that grand unified theories predict, swimming in monopoles, looks nothing like the universe we live in. This was the monopole problem. And for Guth, this was the original puzzle. His notebooks from around 1979 and 1980 show him working specifically on this. How do you get rid of the monopoles? Inflation answers it in the same way it answers everything else. If a phase transition produced monopoles in the very early universe and then inflation happened, the colossal expansion dilutes everything that existed before or during inflation to near nothingness. Take a finite number of monopoles and spread them across a volume that grows by a factor of 10 to the 78th or more, which is what 60 e-folds of expansion gives you in volume terms. And the average density of monopoles in the resulting space is effectively zero, not low, effectively zero. You might expect to find one monopole in a volume many times larger than the observable universe, which is a polite way of saying you'd never find one. Guth's solution to the monopole problem was inflation, and then he realized it was also the solution to the flatness problem, and then that it was the solution to the horizon problem. 3 birds, 1 stone. A stone whose shape he had not entirely understood, but the birds were undeniably dropping. He called his paper Inflationary Universe, a possible solution to the horizon and flatness problems. He published it in 1981, and cosmology quietly began to change. There was one rough edge, though. Guth's original version, what people later started calling old inflation, had a flaw. The mechanism he proposed involved the universe tunneling out of a particular energy state, a bit like a ball rolling over a hill, and the details of how inflation ended and gave way to the ordinary expanding universe we know turned out to produce a very lumpy, inhomogeneous result. Too lumpy. Bubbles of the new phase would nucleate and collide, and the collisions would create a messier universe than the one we live in. The original mechanism for ending inflation was elegant in some ways and broken in others. And that's where, in 1982, 2 refinements arrived, separately, almost simultaneously. The way the best ideas sometimes do in science when the field is ripe and the question is hanging in the air, and more than one brilliant person is pulling on the same thread. Andrei Linde, the same Linde whose filmed reaction to a knock on his door more than 30 years later would become one of the most watched moments in the public life of cosmology, published what became known as New Inflation. Linde's version changed the shape of the energy landscape through which the inflaton field moved. Instead of tunneling through a barrier, the field could slowly roll down a very shallow slope, like a marble moving across an almost perfectly leveled surface. This slow roll made inflation more gradual, more uniform, and, crucially, ended more gracefully without the catastrophic bubble collisions of the original. It gave a smooth exit. Independently, that same year, Andreas Albrecht and Paul Steinhardt, working together, a collaboration, published essentially the same refinement. Slow-roll inflation, the shallow potential, the graceful end. They arrived at nearly the same place by a parallel path, and both papers from 1982 are credited with what the field now calls New Inflation. Steinhardt is an interesting figure to hold in mind. He's one of the architects of the idea that inflation needed to be made better, made to work more smoothly. And decades later, he will be one of inflation's most prominent critics, a founder of the solution who came to question whether the solution was quite what it claimed to be. We'll come back to that. There's time. But for now, inflation, in its new and improved form, has 3 problems solved, a smoother mechanism, and a community of physicists beginning to take it seriously. And it has one more gift that nobody, not even Guth in 1980, had fully recognized yet. The strangest gift, the one that makes the whole thing feel, in retrospect, almost too beautiful and too strange to be real. The galaxies. Let's come at this gently, because it deserves to be arrived at gently. Think about the smallest thing you can imagine, not a grain of sand, that's enormous cosmically speaking, not an atom, smaller than an atom, smaller than a proton, the realm of quantum mechanics, the domain where the ordinary rules of physics quietly dissolve into something altogether weirder. In quantum mechanics, there is no such thing as perfectly smooth emptiness. Even a vacuum, even empty space with nothing in it, nothing at all, seethes with tiny, unavoidable fluctuations. The uncertainty principle, Heisenberg's great gift and great headache, means that you cannot know the state of a quantum field with perfect precision. There will always be jitter, always a flicker of energy that rises and falls at every point in space, at every moment in time. It's not a flaw in the theory, it's fundamental. It's built in. Under ordinary circumstances, which in the universe as it is now, in your room, wherever you are tonight, these quantum fluctuations are invisibly small. They operate at scales so tiny that nothing in the macroscopic world notices them. They come and go and come and go and leave no trace at the scale of anything we can see or touch. But inflation was not ordinary circumstances. During inflation, the universe was expanding so rapidly, doubling and doubling and doubling 60 or more times in that vanishingly brief window, that quantum fluctuations in the inflaton field, the field driving the expansion, were stretched far faster than they could relax back to zero. A fluctuation that would have normally appeared and vanished in an instant was instead pulled outward by the expansion, its wavelength growing until it crossed a particular threshold, what physicists call the Hubble horizon during inflation. And at that point, it froze. It couldn't shrink back down. The expansion was carrying its two ends away from each other faster than any signal could reconnect them, and so the fluctuation was essentially locked in place, stretched and frozen. A quantum hiccup made immortal by expansion. And when inflation ended and the universe settled into its long, slower expansion, those frozen fluctuations became real, physical density variations. Places where the inflaton field had fluctuated slightly high were, when inflation ended, slightly denser than average. Places where it had fluctuated slightly low were slightly less dense, not by much, about 1 part in 100,000. But 1 part in 100,000 spread across the sky in a pattern imprinted by quantum noise stretched to cosmic scale is exactly what we see in the cosmic microwave background. It is exactly, to an astonishing degree of precision, the pattern of hot and cold spots that the COBE satellite first revealed in 1992, that WMAP and Planck later mapped in extraordinary detail. The CMB is not just old light. It is a photograph of quantum fluctuations from the first trillionth of a trillionth of a trillionth of a second, enlarged by a factor almost beyond imagination and held perfectly still for 13.8 billion years until we built instruments sensitive enough to read it. And those frozen density variations, as part in 100,000 quantum noise scaled up, those were the seeds. The small difference between slightly denser and slightly less dense was enough. Over hundreds of millions of years, gravity pulled on those denser regions. Matter fell in. More matter fell in after it. The denser regions grew denser still, while the sparser regions grew emptier. And eventually, long after inflation was over, in a universe already hundreds of millions of years old, those seeds became the first stars, and then the first galaxies, and then the vast filaments and walls and voids of the cosmic web that stretches across the observable universe today. Everything you have ever seen with your eyes or a telescope is downstream of a quantum hiccup in the first instant of existence. The galaxies are frozen quantum noise. The largest structures in the universe grew from the smallest possible fluctuations. There is no more extreme example in all of physics of the microscopic becoming the macroscopic. The quantum world did not stay small. Inflation reached in and pulled it out into the open. This is the spine of the whole story. And it is real. It is not a metaphor, not a popular science simplification, not an analogy offered for comfort in the dark. It is the actual working quantitative prediction of inflationary cosmology. The mathematical machinery connects the quantum jitter to the CMB, to the spectral shape of the fluctuations, to numbers you can measure. Which brings us naturally to the question you might already be quietly forming. If this is all so beautiful, and if the predictions connect so precisely to what we see, then why isn't inflation simply proven? Why are we still hunting a fingerprint? Why, if the galaxies themselves are the evidence, do physicists still hesitate to call the case closed? And that is exactly the right question. Sit with it for a moment, like a puzzle you can feel the edges of but haven't yet assembled. Because the answer lives in a distinction between two kinds of predictions inflation makes, and we need both of them in hand before the story of 2014 and the South Pole and the dust makes its full weight felt. But before we get there, let me give you a moment with the light itself, the canvas. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Laboratories in New Jersey. They had a large antenna, a horn-shaped thing, built originally for communications with early satellites, and they were trying to use it for radio astronomy. And they kept finding noise, a persistent, irritating hiss in the microwave frequencies, coming from everywhere at once, no matter which direction they pointed the antenna. They checked everything. They inspected the equipment. They found inside the antenna horn a pair of pigeons that had taken up residence and left a coating of what Penzias and Wilson diplomatically described in print as white dielectric material, which is to say, pigeon droppings. They cleaned the antenna, they relocated the pigeons, who promptly came back, they relocated them again. They did everything you could do to eliminate the source of the noise. The noise remained. It remained because it wasn't noise. It was the oldest light in the universe. The cosmic microwave background, the afterglow of the hot early universe, released about 380,000 years after the Big Bang, when the cosmos cooled enough for electrons and protons to combine into neutral hydrogen, and space suddenly became transparent for the first time. Before that moment, the universe was a fog, opaque to light. After it, light could travel freely. That first freely traveling light has been traveling ever since. In 13.8 billion years, it has cooled to about 2.725 Kelvin, shifted into microwave frequencies by the expansion of the universe, and it fills every direction of space uniformly. Penzias and Wilson were listening to the birth cry of the universe, muffled by 13 billion years and mistaken for pigeon droppings. They won the Nobel Prize in Physics in 1978. The CMB, once identified, became the most important single observable in cosmology, because it's not just old light, it's old light with information in it, tiny temperature variations. That one part in 100,000 we've been talking about, imprinted when the universe was 380,000 years old, carrying the signature of everything that happened before. Everything set up during inflation, everything written in the density fluctuations, frozen from quantum jitter. All of it recorded in the temperature and polarization of this ancient glow. In 1992, NASA's COBE satellite, the Cosmic Background Explorer, made the first maps of those tiny variations. John Mather and George Smoot led the effort, and what they found confirmed a fundamental prediction. The fluctuations were there at the expected level with the expected broad statistical properties. Mather and Smoot shared the Nobel Prize in Physics in 2006 for this work. It was one of those moments in science when a prediction made years before the technology existed to test it turned out to be right. WMAP followed COBE. The Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped the CMB in far greater detail and gave cosmologists the first precise measurements of many of the universe's fundamental properties. And then Planck, the European Space Agency's Planck satellite, which operated from 2009 to 2013, mapped the CMB in finer detail still, with greater sensitivity across more frequency channels, producing maps of extraordinary precision that allowed the testing of inflationary predictions with a rigor that Guth in 1981 could not have imagined. And here is where the story of the confirmed predictions begins. Because the Planck data do not merely say, yes, the universe is roughly as inflation predicts, they say something much more specific, something that requires a number. The quantum fluctuations stretched during inflation, the seeds of structure, are predicted to have a particular statistical shape, a particular way of being distributed across different scales. Not all scales should carry the same amount of power. Inflation predicts a slight preference for larger scales over smaller ones. The fluctuations should be what physicists call nearly but not exactly scale invariant. A perfectly scale invariant spectrum would have a spectral index, denoted n sub s, equal to exactly 1. Inflation predicts n sub s slightly less than 1. The slow roll during inflation, the details of how the inflaton field was rolling down its potential as it was producing fluctuations, imprints this slight tilt. Planck measured n sub s, the result, approximately 0.965, not 1, not slightly different from 1 in some general hand-wavy way, a specific number, 0.965, significantly and measurably below 1, in the direction inflation predicts by roughly the amount inflation predicts for the broad class of slow-roll models. Inflation made a number, reality matched it. And then there's the flatness, the curvature parameter omega sub k measured from the cosmic microwave background and the large-scale distribution of galaxies, consistent with 0 to within about 0.5%. Space is flat, exactly as inflation requires, and the fluctuations are Gaussian, bell curve distributed, random in the way quantum noise should be random, and they are adiabatic, all components of the early universe, matter and radiation, fluctuating together. Both confirmed by Planck data. Both predictions of the simplest inflationary models. These are genuine successes. These confirmed predictions are why the cosmological community treats inflation not as a wild speculation, but as the working paradigm, the framework within which models are built and tested. When you ask, why do physicists believe in inflation? These are the answers. Not faith, not aesthetics. Numbers predicted in advance, then measured, and yet, something is missing from that list. The most important thing, the thing that would convert very well-supported leading framework into confirmed. The thing that would tell us not just that inflation happened in some general sense, but what it actually was, how energetic, how the inflaton field was shaped. The fingerprint, the one that's still out there. And here, I need to ask you to stay with me just a little longer before we sleep, because this part matters, and it's genuinely beautiful and genuinely unresolved, and we're right at the edge of it now. Those density fluctuations, the scalar perturbations, the quantum noise stretched and frozen that seeded the galaxies, those are one kind of ripple the inflaton field produced during inflation. But there is another kind. Quantum mechanics operating during inflation didn't just ripple the inflaton field, it also rippled space-time itself. The geometry of space, the fabric underneath everything, was quantum jittery too, and inflation stretched and froze those space-time ripples just as it stretched and froze the density variations. Those frozen ripples in space-time are gravitational waves, not the gravitational waves that LIGO detected in 2015, the ones generated when two massive black holes spiral together and merge. Those are local, recent astrophysical events, and the waves they make are relatively short, relatively strong, and completely different in character. The primordial gravitational waves left over from inflation would be far longer in wavelength, far older, and unimaginably faint by now, having been traveling and stretching with the universe for 13.8 billion years. You cannot detect them directly with a machine like LIGO. They are far too faint, but they leave a trace, a specific, distinctive trace in the light we can see. The cosmic microwave background is not just a map of temperature, it is also, in principle, a map of polarization. The light waves of the CMB are not randomly oriented. They have preferred directions of oscillation that were set by the physics of the early universe, the way the photons last scattered off matter just before the universe became transparent. And the pattern of polarization carries information. It carries two distinct types of pattern. There is a gradient pattern, a curl-free pattern mathematically similar to the field around a point charge that physicists call E-mode polarization. And there is a curl pattern, a rotational pattern, mathematically similar to the field around a bar magnet called B-mode polarization. Density fluctuations, the quantum noise that seeded the galaxies, the scalar perturbations, those produce E-mode polarization in the CMB. Only E-modes, the gradient pattern, the curl-free one, primordial gravitational waves, the space-time ripples frozen from quantum jitter during inflation, the tensor perturbations, those produce both E-modes and B-modes, including that distinctive curl, that rotational pattern. There are other things that can produce B-modes: gravitational lensing, the bending of CMB photons by the large-scale structure of the universe as they travel to us, converts some E-modes into B-modes, and this lensing signal has been detected and measured and is part of the standard picture. And as 2014 would teach the world in the most dramatic possible way, polarized dust from our own galaxy can mimic B-modes too. But primordial B-modes are the B-mode signal at large angular scales, the pattern that would come from gravitational waves produced in the very first instant of inflation. That would be the one signal you could not fake with anything that happened after inflation ended. The one signature that points unambiguously back to the moment before everything else began. This is why they are called the smoking gun of inflation. Not because every other prediction isn't good evidence, they are, but because the B-mode signal from primordial gravitational waves would be direct physical proof that space-time itself was quantum jittery during inflation, that the energy scale of inflation was high enough to produce observable tensor perturbations, that the specific model of inflation was of a particular kind. It would transform inflation from an extraordinarily well-supported framework into a confirmed physical theory. It would be, in the judgment of most cosmologists, a Nobel Prize. The strength of this signal is described by a single number, the tensor-to-scalar ratio, R. The ratio of the power in gravitational waves to the power in density fluctuations. A large R means inflation was energetic, the inflaton field was high up on a steep potential, the expansion was furious, and the B-mode signal would be larger and easier to detect. A small r means inflation was gentler, and the B-mode signal is fainter. Here is what makes detecting R so staggering in its implications. The energy scale of inflation is, in most models, somewhere around 10 to the 16th giga-electron volts. If you can measure R, you're probing the physics of a particle physics energy scale roughly 1 trillion times higher than the center of mass energy of the Large Hadron Collider in Geneva. The LHC smashes protons together at energies of trillions of electron volts. The inflationary energy scale is 1 trillion times higher than that. We will never build a particle accelerator that reaches inflationary energies, not in any conceivable human future. The CMB is the only instrument that probes that realm. If we read R out of the CMB polarization, we will have done particle physics. Real, quantitative, constraining physics, at an energy our machines can never touch. The universe's first instant is the only laboratory for the universe's first instant, and it left its notes in the oldest light. This is why the hunt matters so much. This is why in 2014, when a team reported that they had found the signal, it felt like one of the great moments in the history of science, and why, in the months that followed, when it became clear they hadn't, when the dust claimed what the astronomers had hoped to celebrate, the silence that replaced the cheering was so particular, so heavy with what might have been. But that story is just ahead of us now, just past the edge of this quiet darkness. The South Pole is waiting. The telescope is already pointing at the sky. The cold is extraordinary. And somewhere in the data, a pattern that looked for weeks like the answer to everything. So let us stay here for a moment, in this quiet space between what inflation promises and what we've actually managed to confirm. Because this is where the story gets genuinely interesting. Not just the extraordinary claim that a quantum shiver became a galaxy, but the fact that inflation has made specific, testable, numerical predictions, and we have gone out and checked them, and some of them have come back correct in the most satisfying way science can deliver. That matters. It's worth slowing down for, because when a theory predicts a number before you measure it, and then you measure it and find that number waiting for you, something real happened. Something more than coincidence. Something that deserves to sit quietly with you for a moment before you drift off. So here is what inflation predicted, and here is what we found. The first thing is something called the spectral index. And the name sounds technical, but the idea behind it is almost beautiful in its simplicity. When inflation stretched those quantum fluctuations out to cosmic scale, when it took the microscopic jitter of the inflaton field and blew it up until it was big enough to become the seeds of galaxies, it didn't do so in a perfectly even-handed way. Not every scale got exactly the same amount of power. The mathematics of the process predicted a slight preference. Larger scales, the scales that would one day become the biggest structures in the universe, would carry just a little more energy than smaller ones. Not a lot, a slight tilt, a lean. And this tilt is measurable. It shows up in the pattern of hot and cold spots on the cosmic microwave background, in the way fluctuations at different angular scales relate to each other. And physicists had worked out before they measured it what that tilt should be. They gave it a number, the spectral index, written as NS. A perfectly scale-invariant universe, one where every scale gets identical treatment, would have NS equal to exactly 1. But inflation predicted something slightly less than 1, a specific, measurable deviation from perfect uniformity, a tiny, definite lean toward the large. When the Planck satellite measured it, and Planck is the most precise instrument we have ever built for reading the cosmic microwave background, a satellite that mapped the whole sky with extraordinary care, the measurement came back as approximately 0.965, not 1, 0.965, measurably, significantly less than 1, which is exactly where inflation had told us to look. Think about what that means. Physicists working through the mathematics of a process that happened in the first 10 to the minus 32nd seconds of time predicted a number. And when we built a satellite and listened to the oldest light in the universe, the light gave us back essentially that number. The tilt was there. The lean was real. The universe had been keeping the receipt. Now one number matching is suggestive, but not conclusive. You'd want more, and inflation gives you more. The second confirmed prediction is flatness, and this one deserves its own little moment, because it's one of those things that sounds obvious until you realize it isn't. When cosmologists talk about the flatness of the universe, they don't mean flat like a table. They mean something more abstract, the geometry of space itself on the very largest scales. Space can be positively curved like the surface of a sphere. On a sphere, if you draw a triangle, the angles add up to more than 180 degrees. Space can be negatively curved like a saddle, where the angles of a triangle add up to less than 180 degrees. Or space can be flat, perfectly Euclidean, where triangles behave the way your geometry teacher told you they would, and the angles add up to exactly 180 degrees. The question of which kind of universe we live in is not a question of shape in any everyday sense. It's a question about the total energy content, how much matter and energy there is compared to what's called the critical density. If you're right at the critical density, space is flat. If you're above it, space is positively curved. Below it, negatively curved. And here is the thing, there's no obvious reason the universe should be flat. The standard Big Bang picture without inflation gives you no particular expectation of flatness. A universe that starts with curvature tends to grow more curved over time, the way a ball balanced on a hilltop will roll one way or the other rather than staying at the top. For space to be as flat as it appears today, It would have had to be fine-tuned to an extraordinary precision in the very beginning, balanced on that hilltop with such delicacy that it boggles the mind. Inflation offers an explanation. When you expand a region by a factor of e to the 60 or more, you flatten it. Think of the surface of a balloon. Before you inflate it, the surface might be crumpled and curved in all kinds of ways. But blow it up, stretch it enormously wide, and locally the surface looks flat. The curvature is still there in principle, but it's been stretched to scales so large that locally you can't see it. Inflation does this to space itself. Whatever curvature the universe had before inflation, inflation dilutes it to the point of near-perfect flatness. So inflation predicts, measure the geometry of space, and you should find it flat, not approximately flat, extremely, precisely flat. And when we use the cosmic microwave background as a kind of cosmic ruler, comparing the actual angular size of those hot and cold spots to what their physical size should be based on the known physics of the early universe, what we find is space that is consistent with perfect flatness to within about 0.5%. The curvature parameter, written as omega k, is constrained to be approximately 0 plus or minus about 5 thousandths. The universe is, to the limits of our measurement, geometrically flat, exactly as inflation requires. That's two specific predictions, each requiring a number to match, and both of them matching. The tilt is there, the flatness is there. There is a third, which is perhaps more subtle, but no less real. Inflation predicts that the fluctuations it generates should be Gaussian. That is, they should be distributed in a bell curve, random noise of a particular statistical character, with no preferred patterns or special correlations baked in. And they should be what's called adiabatic. All the different components of the universe, the photons and the dark matter, and the baryons, all fluctuating together in step rather than in separate independent ways. When we search the cosmic microwave background for violations of these properties, for signs that the fluctuations are non-Gaussian or non-adiabatic, for hidden structure that doesn't match inflation's prediction, we find nothing. No deviations at the level that would challenge inflation. The fluctuations look exactly as Gaussian and adiabatic as the simplest inflation models say they should. Taken together, these confirmed predictions, the spectral index NS at approximately 0.965, the spatial flatness, the Gaussian and adiabatic character of the perturbations, mean that inflation is not hand-waving. It is not a story we tell because it sounds plausible. It is a framework that makes specific, falsifiable, numerical claims, and some of those claims have been checked and found correct. That is the definition of a theory earning its place. Inflation has earned some of its place, but here is the honest tension. And this is where we need to stay a little while, because this tension is the heart of the whole video. There is a difference between confirmed predictions and confirmed proof. Inflation has confirmed predictions. It does not yet have confirmed proof. The three things we just described, the tilt, the flatness, the Gaussianity, are necessary conditions. They are what inflation requires. But they might not be sufficient. It's at least conceivable that some other framework, some theory we haven't written down yet, could also produce those features. Inflation predicts them. That doesn't automatically mean that nothing else could. What would close that gap? What would constitute the smoking gun, the thing that not only matches inflation's predictions but could essentially only come from inflation? That is where the fingerprint comes in, the real fingerprint, the one we have not yet found. And to understand it, you need to know about a second kind of fluctuation that inflation produces. We've talked about the density fluctuations, the scalar perturbations, the ripples in how much matter is clumped in different places, the seeds of galaxies and clusters and voids. Those are confirmed. We can read them in the cosmic microwave background. They're real. But inflation is not subtle. It's a violent, extraordinary process, an exponential expansion of space-time itself. And space-time, when it's shaken that hard, doesn't just ripple in density, it ripples in geometry. Space-time itself develops waves, ripples in the fabric, stretches and compressions, propagating through the structure of space and time themselves. These are called gravitational waves, but not just any gravitational waves. Now, before we go further, and this is important enough to pause on, you may have heard about gravitational waves in a different context. In September 2015, a pair of enormous detectors called LIGO, the Laser Interferometer Gravitational Wave Observatory, detected a gravitational wave for the first time. The announcement came in February 2016, and it was one of the great moments in observational physics. Two black holes, each many times the mass of our Sun, had spiraled together and merged somewhere about 1 billion light-years away, and the collision sent ripples through space-time that crossed the universe and, on September 14, 2015, flexed the mirrors inside LIGO's arms by a distance smaller than a proton. That was extraordinary. That was real. That detection absolutely deserves every bit of its place in history. But those gravitational waves are not the gravitational waves we're hunting in the cosmic microwave background. They are not the same kind of thing. LIGO's waves were produced recently on cosmic timescales, 1 billion years ago by two objects smashing together in a violent astrophysical event. They were short in wavelength, arriving as a brief chirp, a fraction of a second from start to finish. They were local, from a specific event in a specific place. The primordial gravitational waves that inflation would have produced are something else entirely. They are tensor perturbations, fluctuations not in the density of matter, but in the geometry of space-time itself, generated everywhere and all at once in the first 10 to the minus 32 seconds of time, stretched like the density fluctuations to cosmic scale, made permanent, woven into the structure of the universe. These waves have wavelengths as large as the observable universe itself. They have been traveling, if you can even call it that, since the beginning of everything, and they are so faint, so stretched and diluted by 13.5 billion years of cosmic history that no detector like LIGO could ever hope to directly sense them. They are far too large and far too quiet for any instrument you could build on the ground. But they are not completely silent. They leave a trace. And the trace is written, like everything else important about the universe's beginning, in the cosmic microwave background. Here is how it works, and this is the part where you might want to settle your head a little deeper into the pillow, because this is worth following slowly. Light has polarization. When you hold up polarized sunglasses, you're filtering light waves based on the direction they're oscillating. Light can oscillate in different directions, horizontally, vertically, diagonally, and that orientation is its polarization. The photons that make up the cosmic microwave background are polarized too. They were polarized in the early universe by the process of scattering, photons bouncing off electrons in the hot plasma before the universe cooled enough for atoms to form, picking up polarization patterns based on the temperature differences around them. Now, those polarization patterns have shapes. Mathematically, cosmologists decompose the polarization of the CMB into two kinds of patterns. One is called E-mode polarization, the other is called B-mode polarization. The names come from electromagnetism, E for electric field patterns which have no curl, B for magnetic field patterns which do. An E-mode pattern in polarization is a gradient. It flows outward or inward, like the field lines of an electric charge. A B-mode pattern is a curl, twists around a point the way water spirals down a drain. The key physics is this: the density fluctuations, the scalar perturbations, the seeds of galaxies can only produce E-mode polarization. They squeeze and stretch space in a way that gives you gradient patterns but no curl, no B-modes. Scalar perturbations alone cannot make a curl. Primordial gravitational waves, the tensor perturbations from inflation, can. They stretch space-time alternately in two directions, rotating in a way that imprints a curl directly onto the polarization of the photons traveling through them. They make B-modes. Specifically, they make B-modes at large angular scales, the big sweeping patterns across the sky. This was worked out in 1997 independently by two groups of theorists, Mark Kamionkowski, Arthur Kosowski, and Albert Stebbins on one side, Uroš Seljak and Matías Saldarriaga on the other. Both groups published in 1997 essentially simultaneously, and between them they established something beautiful and exact, a detection of large-scale B-mode polarization in the cosmic microwave background would be an unambiguous signal of primordial gravitational waves from inflation. Not just a hint, not just a suggestion, an unambiguous signal. Nothing else should produce those B-modes at those large scales, not galaxy formation, not dark matter clumping, not any known astrophysical process generates a primordial B-mode at the angular scales we'd be looking for. If you see it, it means gravitational waves from inflation. If you see it, you're reading the birth cry of the universe. This is what makes it the smoking gun. This is what makes B-mode polarization different from the other confirmed predictions. The spectral index and the flatness could, in principle, be mimicked by other frameworks. A large-scale B-mode signal in the CMB at the right amplitude and pattern cannot. It is inflation's specific, forgeable signature, the fingerprint, and the strength of that signal, how pronounced the curl pattern is, how clearly it rises above the background noise, is what the tensor to scalar ratio, R, quantifies. The ratio of the gravitational wave power to the density fluctuation power. A large R means strong gravitational waves, a strong signal, easier to find. A small r means weak waves, a faint signal, harder to find. And, this is the beautiful physics, the value of r is directly related to the energy scale of inflation. Higher energy inflation produces more gravitational waves, a bigger r, lower energy, smaller r. So if you measure r, if you find the B-modes and pin down their amplitude, you're doing something no particle accelerator can do. You're measuring the energy at which the inflationary process operated. The mathematics works out to an energy scale of around 10 to the 16th Geiger-electron volts for the simplest high R models. To give you a sense of scale, the Large Hadron Collider at CERN, the most powerful particle collider ever built, operates at energies of a few trillion electron volts in center of mass terms, a few thousand giga-electron volts. The inflationary energy scale is roughly 1 trillion times higher than that. Not 100 times, not 1,000 times, 1 trillion times. We will never build a machine that reaches that energy. There is no engineering path, no conceivable future civilization that builds an accelerator probing the inflationary energy scale directly. The physics of that regime, whatever field drove inflation, whatever particle physics symmetries were operating at that moment, whatever lies at the heart of grand unified theories, that physics is behind a door we cannot open with any machine on Earth, except that the universe, obligingly, ran the experiment for us. It ran the experiment at 10 to the minus 32 seconds, and it wrote the results in the oldest light. If we can read R out of the cosmic microwave background polarization, we will have done quantitative physics at an energy scale our machines can never touch. We will have turned the CMB into the highest energy particle physics experiment ever conducted. That is what the fingerprint would give us, not just confirmation that inflation happened, a window into the physics of the very beginning, a number that constrains which of the many, many proposed inflation models actually describes our universe. And so in the years after Kamionkowski and Kosowski and Stebbins, After Seljak and Zaldariaga, teams of experimentalists began to think seriously about how to find it, to build instruments sensitive enough to detect B modes in the polarization of the cosmic microwave background, to go somewhere cold and dry and still, somewhere the atmosphere wouldn't absorb and scatter the faint microwave signals, and point a telescope at the sky and look for the curl. The South Pole is the driest place on Earth in terms of precipitable water vapor. The thin, clear, bitter air there is nearly transparent to microwaves in a way that no other easily accessible location on Earth quite matches. It is extraordinarily cold, which reduces thermal noise in the detectors. It is a hostile and remarkable place to do science, and it has become one of the great observatories of the modern age. And it was at the South Pole that BICEP 2 was built. BICEP stands for Background Imaging of Cosmic Extragalactic Polarization, a name that tells you exactly what it is doing. The BICEP program had run an earlier version, BICEP 1, proving the concept, refining techniques, learning the sky. BICEP 2 was a more sensitive instrument with hundreds of detectors carefully engineered to measure the polarization of the microwave background with extraordinary precision. The team spent years collecting data, checking and rechecking, looking for the pattern. And what they were looking for is subtle enough that it's worth making sure you can picture it. The whole sky in microwave light is nearly uniform. The 2.725 Kelvin glow of the afterglow of the Big Bang, the relic radiation that Penzias and Wilson found by accident at Bell Labs in 1964 and 1965, the noise they first thought was pigeon droppings in their antenna before realizing it was the afterglow of creation itself. But mapped at finer scales, as Kobe did in 1992, earning John Mather and George Smoot a Nobel Prize in 2006, and as W. Mapp and then Planck refined further, that light has tiny temperature fluctuations, 1 part in 100,000, the seeds of all structure. And it is polarized. The polarization is faint. The B-mode component, if it exists, is fainter still. You are looking for a curl pattern in the polarization of light that has been traveling for nearly 14 billion years, imprinted by ripples in space-time that existed for a fraction of a fraction of a fraction of a second. The signal, even in the most optimistic inflation models, is many times fainter than the dominant E-mode polarization from density fluctuations. You need an instrument of remarkable sensitivity. You need to observe for a long time. You need to understand everything else that could produce a similar pattern and make sure you're not being fooled by it. That last requirement, understanding everything else that could produce a similar pattern, turned out to be the crux of everything. Because here is the uncomfortable truth about the microwave sky. It is not just the cosmic microwave background out there. There is other stuff in the way. Our own galaxy, the Milky Way, emits microwave radiation, and some of that radiation is polarized. The mechanism is this: interstellar space is not empty. It is threaded with magnetic fields. The Milky Way has a large-scale magnetic field, tangled and complex, but with a definite structure. And floating through that space are tiny grains of dust. Not the comfortable metaphorical dust of everyday life, but actual microscopic particles, elongated grains of silicates and carbon compounds, some of them no bigger than a few hundred atoms across. These grains tend to align with the ambient magnetic field like tiny compass needles settling along the field lines over time. When those aligned grains are warm, they emit thermal radiation, including microwaves. And because the grains are aligned, the radiation they emit is polarized, preferentially oscillating in a particular direction related to the grain's orientation and the field direction. This polarized emission from aligned interstellar dust grains is a foreground signal. It sits between us and the cosmic microwave background, and it contributes its own polarization pattern to the sky we observe. And crucially, that foreground pattern can include curl. It can include B modes, not because of anything cosmic or primordial, just because the complex tangled geometry of the Milky Way's magnetic field and the dust grains aligned to it can produce polarization patterns that, when analyzed, contain a curl component. Galactic dust can mimic or swamp or contaminate the cosmological B-mode signal we're looking for. This was known in principle before BICEP 2 made its announcement. The question was always how much dust. How polarized is it in the particular patch of sky BICEP 2 was observing? How big is the foreground contamination compared to the signal? The BICEP 2 collaboration knew they needed to estimate the dust, and they did their best, but they were limited by the data available to them. The Planck satellite, which was observing the full sky at multiple frequencies simultaneously, had information about polarized dust. But Planck had not yet publicly released its polarized dust maps in the frequency range that would be most useful for estimating foregrounds in the BICEP 2 field. What was available reportedly was a preliminary result shown in a presentation at a conference. Numbers from a slide, informally obtained, used to estimate how much dust BICEP 2 might be seeing. That estimate, it would turn out, was too low. But we are not quite there yet. Let us stay for one more moment in the time before March 17th, 2014, when the data is still being analyzed, when the signal is still holding up, when the team is still working through the checks and the cross-checks, when the curl pattern in the polarization is still sitting in the data, looking real, looking strong, pointing at a tensor to scalar ratio of approximately 0.20. An R of 0.20 would have been an extraordinary number. Strong, loud, easy to see once you had the sensitivity. It would have meant that the gravitational wave contribution to the CMB was large, that inflation had operated at a high energy scale, that the simplest, most dramatic inflation models were right. It would have been the smoking gun. Clear and unambiguous and enormous, and it would have meant something else too. It would have meant that for all the years of searching, for all the careful work and the long cold nights at the South Pole, the answer had been there in the data, waiting to be read. That the fingerprint of the universe's first instant had been found, that the oldest light in the universe had finally, at last, given up its deepest secret. That is what the team believed they had found. That is what they reported to the world on March 17th, 2014, at a press conference at the Harvard-Smithsonian Center for Astrophysics. And in the hours and days that followed, the reaction from the scientific community and from the wider world that pays attention to these things was unlike almost anything in modern cosmology. It felt, for a brief and extraordinary moment, like one of those rare occasions when a fundamental question about the universe gets answered. Not partially answered, not constrained, answered. Here, in this data from a telescope at the bottom of the world, was the first direct evidence of cosmic inflation. The first direct evidence of primordial gravitational waves, proof that quantum gravity effects had left observable imprints on the universe. Proof that the birth cry of everything had been heard. And there is a moment from those days that became, briefly, one of the most widely watched clips in the public history of science. A video, filmed by members of the BICEP 2 team, of them going to Andrei Linde's home. Linde, one of the architects of inflation, the man who had developed what's called new inflation in 1982, who had spent decades refining and defending the theory and thinking about its predictions and its implications. Linde being told at his door that it had been confirmed, that his life's work had been vindicated, that the signal was real. He cried. And the footage of that moment, the emotion on his face, the weight of a lifetime of theoretical work suddenly touching the real world, traveled around the internet and through news reports and into the broader cultural conversation about what it looks like when science works, when the abstract becomes concrete, when the math touches the universe. For weeks it seemed like that was the story. The discovery of inflation's smoking gun, probably a Nobel Prize. A new chapter in the history of cosmology. And then the questions started. Careful readers of the paper noted the dust estimate, the single observing frequency, the difficulty of separating a cosmological signal from a galactic foreground when you're working at only one wavelength. Dust is brighter at higher frequencies. Synchrotron radiation, another galactic foreground from energetic electrons spiraling around magnetic field lines, is brighter at lower frequencies. The cosmological B-mode signal sits beneath both. To cleanly pull it out, you need multiple frequency channels, so you can model the foreground emission and subtract it, leaving only the cosmological component behind. BICEP2 had observed at 150 GHz, one frequency, and the dust estimate they had used, that number from the conference slide, was, in the words of the subsequent analysis, inadequate. In September 2014, the Planck collaboration published a dedicated measurement of polarized dust emission across the sky, including in the BICEP2 observing field. And the news was not good. The polarized dust in that region of the sky was higher than the BICEP2 team had assumed, high enough, in fact, to account for a significant portion, possibly all, of the claimed signal. The definitive answer came in early 2015 when the BICEP2 team and the Planck team conducted a joint analysis together. They combined their data, BICEP2's sensitivity and sky coverage at 150 GHz, Planck's multi-frequency information about the foreground dust, and did what the single-frequency result could not do, properly subtracted the dust. When the dust came out, the signal went with it, or rather, the remaining signal, whatever was left after the foreground subtraction, it was consistent with zero. The data did not show statistically significant evidence for primordial gravitational waves. The tensor-to-scalar ratio consistent with the dust-subtracted data was consistent with an upper limit, not a detection. The R0.20 that had briefly shone like a confirmation of everything evaporated into noise. The discovery was retracted. Not in a scandal, not through fraud. The collaboration had done what they could with the data they had, and they acknowledged the limitation and worked transparently with Planck to get the right answer. But the result was gone. The moment was over. Andrei Linde was not vindicated that year, and somewhere in the public understanding of science, a quiet settling took place. The reporters who had written the discovery stories wrote the correction stories. The video of Linde at his door was still there on the internet, still moving, but now carrying a different weight. Not triumph vindicated, but hope deferred. Not the answer. The near miss. It is important to say clearly, this did not disprove inflation. The retraction of a detection is not the confirmation of the opposite. The dust swamping the signal does not mean the signal isn't there. It means the signal, if it's there, is smaller than 0.20. It means we need more sensitivity and better foreground control. It means the fingerprint is fainter than we hoped. That's a fact about the universe, not a failure of the theory. But the episode left something important behind, a lesson and a constraint. The lesson is in how the mistake was made, the danger of announcing a discovery before the foreground contamination is properly characterized, the danger of single-frequency observation in a regime where multiple foregrounds overlap with the signal. The danger of press conferences before peer review has wrestled with the hardest questions. Science is self-correcting, and BICEP2 corrected itself. But the correction took months and came at a cost to public trust that the community felt deeply. And the constraint is real when the dust was properly accounted for, and when subsequent observations with better data sets tightened the limits further. The current state of the art coming from what's called the BK18 dataset, combining BICEP and the Keck array with Planck's multi-frequency information. The upper limit on the tensor-to-scalar ratio settled to R less than 0.036 at 95% confidence. That number, that upper limit, is not nothing. It is not a failure. It is science in progress, because an upper limit is a constraint, and a constraint rules things out. And what it rules out is significant. Some of the inflation models that seemed most natural, most elegant, in the years after Guth and Linde first wrote them down, they've been quietly eliminated by this non-detection. Not disproven by a competing idea. Not abandoned because physicists got bored. Eliminated by the simple, stubborn fact that if they were right, we would have seen something by now, and we haven't. The clearest example is one of the oldest and simplest versions of the theory, when Andrei Linde developed what he called chaotic inflation. The idea that the inflaton field starts in some random, high-energy configuration and just rolls down slowly, like a ball rolling down a very gentle slope. The most natural mathematical form for that potential was a quadratic one. Physicists write it as m squared phi squared. It's the simplest possible shape, a parabola, and that simplest shape makes a specific prediction, a tensor to scalar ratio r somewhere in the range of about 0.15 to 0.20, a signal that BICEP2 era instruments should have been able to detect. But we didn't detect it, and the upper limit now, r less than 0.036, sits well below what that model predicts. Which means the simplest version of Linde's own most celebrated contribution to inflation is now, to put it plainly, ruled out. Not by a philosopher's argument, not by a clever theoretical objection, by the data, by the dust-subtracted, multi-frequency, carefully analyzed data that came back from South Pole telescopes and a satellite orbiting above the murk of our own galaxy's foreground glow. There is something quietly extraordinary about that. A man spends decades developing one of the most sweeping ideas in the history of science. He is filmed, in 2014, crying with something that looks like relief and joy when a team of researchers arrives at his door to tell him they've found the proof. And then, in the years that follow, the very non-detection of that proof erases the simplest, most natural version of his idea. The universe, it turns out, is more particular than the most elegant first guess. Whatever inflation was, its energy landscape was not a perfect parabola. The shape of how creation unfolded is more subtle than that. That is a genuine scientific result. A hard-won, specific, true thing that nobody knew before BICEP2 and its successors started looking with the precision they brought to the question. And it opens another one, because if the simplest models are gone, what remains? What inflation models are still standing, still consistent with R less than 0.036? Quite a few, actually. The so-called Starobinsky model, which was written down by the Russian physicist Alexei Starobinsky as far back as 1980, predicts R of roughly 0.03 to 0.04, far below the current limit, and interestingly right in the sweet spot that the next generation of instruments is being built to probe. Models with what physicists call plateau potentials, inflatons that roll along a very flat, nearly level region of their energy landscape before eventually falling off, tend to predict small values of R consistent with everything we've measured so far. These are the models that survive. These are the ones that Lightbird will either confirm or kill. So the non-detection is not the end of the story. It's a chapter that eliminated some theories and focused the search. That is exactly how science is supposed to work, even when it's uncomfortable, even when the simplified version doesn't have a tidy hero finds the answer arc. Now here, it's worth pausing, because there is a voice in this conversation that deserves to be heard, a voice that pushes back not just on this or that inflation model, but on the entire program. Paul Steinhardt, one of the physicists who helped develop the new inflation picture in 1982 alongside Andrei Linde and Andreas Albrecht, has become one of inflation's most persistent and prominent critics. He didn't walk away from the field, he turned around inside it. And in the years since, particularly in work with Anna Ijas and others, Steinhardt has raised what he considers a fundamental problem, that inflation, as a framework, may not be falsifiable in the way a good scientific theory needs to be. The argument goes something like this. Inflation isn't a single specific model, it's a family of models, a broad class of theories that all invoke some version of a rapidly expanding epoch driven by some inflaton field. And that family is large, very large. Different inflation models predict different values of R, different tilts of NOS, different levels of non-Gaussianity, different things about the universe's large-scale structure. When a specific model's prediction conflicts with data, as the m² phi² potential has, physicists don't abandon inflation. They find another model within the family that still fits. And because the family is so large and so flexible, Steinhardt and his colleagues worry that it can accommodate almost any observational outcome. A theory that can explain anything, the argument goes, actually explains nothing. It's not a prediction, it's a retrodiction. This is a genuine philosophical and methodological critique, and it comes from someone who was there at the beginning. It is not crankery, it is a legitimate scientific debate that is ongoing, that appears in serious journals and serious conferences, and that the cosmology community takes seriously even where it disagrees. Steinhardt himself has championed an alternative, bouncing cosmologies, and in particular cyclic models, pictures of the universe in which the Big Bang is not a beginning but a transition, a bounce from a prior contracting phase in an endless cycle of expansion and contraction, separated by moments of something like collision between higher dimensional structures that physicists call branes. In these models, the large-scale structure of the universe, the smoothness, the flatness, the pattern of fluctuations arises not from a sudden violent burst of inflation, but from a very long, slow, contracting phase before the bounce. These are serious theoretical proposals. They face their own challenges. The physics of the bounce itself is not well understood, and cyclic models make their own predictions that can, in principle, be tested. But the crucial point for our purposes tonight is this. Cyclic models and some other bouncing alternatives generally predict a very small or negligible amount of primordial gravitational waves, a very small or zero R, which means that if light bird flies and if it searches with its extraordinary sensitivity of delta R less than 0.001, and if it finds nothing, finds that R is not just less than 0.036 but less than 0.001, consistent with zero within the measurement's noise, that result will simultaneously be consistent with Steinhardt's cyclic alternatives and with the plateau potential inflation models. Non-detection at that level would not be able to definitively distinguish between them. But if light bird finds something, if somewhere between R equals 0.001 and R equals 0.036 a real signal emerges, a genuine primordial B-mode curl in the oldest light, surviving every foreground subtraction at every frequency, clean and consistent across the sky, then the cyclic models, at least in their current form, would be in serious trouble. And inflation, after 40 years of supporting evidence without its smoking gun, would finally have the thing that makes it more than a well-supported hypothesis. That is the stakes of the search, one fingerprint, one number. And depending on what that number turns out to be, or whether it exists at all, the entire picture of what happened in the universe's first instant could shift in a fundamental way. So let's talk about who is going to look for it, and how. The lesson of Bicep 2 was written in dust, literally. And the experiments that come after it have been designed with that lesson at the center of everything they do. The problem, to put it simply, is this. When you point a telescope at the sky and try to measure the polarization of the cosmic microwave background, you're not seeing a clean, pristine signal from 13 billion years ago. You're looking through our own galaxy. And our galaxy is full of things that also emit polarized microwaves. Interstellar dust, those tiny grains of silicate and carbon floating between the stars, aligned by the Milky Way's magnetic field into something like a vast, loose lattice, glows in the microwave frequencies. And because the grains are aligned, their emission is polarized. Not randomly, but in organized patterns that, when you look at them from a distance, can mimic the swirling curl of a B-mode signal. The pattern isn't identical and it's not uniform across the sky, but it's similar enough and bright enough in some regions that a telescope measuring at a single microwave frequency cannot reliably tell the two apart. Dust emission gets stronger as you go to higher microwave frequencies. It's brighter at 217 GHz than at 150, and brighter still at 353 GHz. There's also another foreground, synchrotron radiation, which comes from high-energy electrons spiraling through the Milky Way's magnetic field. Synchrotron emission goes the other way. It's brighter at lower frequencies, dimmer at higher ones. Between them, there's a kind of window, a frequency range, somewhere around 70 to 150 GHz, where both foregrounds are relatively faint, and the cosmological signal, if it's there, has its best chance of being the dominant thing you're measuring. But even in that window, the foregrounds don't disappear, they just decrease. The only way to separate them from the signal you actually want is to observe at many different frequencies. At high frequencies, you're predominantly measuring dust, so you can build a model of the dust's spatial structure and brightness. At low frequencies, you're predominantly measuring synchrotron, and at the frequencies in between, where the cosmological signal is strongest relative to both foregrounds, you can subtract the models you've built from the measurements you've made and look at what's left. If what's left is consistent with a B-mode polarization pattern at large angular scales, the scale where primordial gravitational waves would leave their mark, then you have something real, or at least something that survived the foreground subtraction, which is the closest thing to real that careful science can offer. BICEP 2 observed at 150 GHz, one frequency. It was not equipped to separate foreground from signal by this multi-frequency method. The dust model it used was not derived from dedicated matched sky measurements. It was pieced together from what was available, including, according to accounts of the period, a preliminary sky map presented at a Planck collaboration meeting, a map shown in a conference talk, not yet formally published, which BICEP 2 team members reportedly used to estimate the dust contamination in their observation field. That estimate turned out to be too low. When the Planck satellite, which observed the entire sky at 9 different frequency bands from 30 to 857 GHz, finally released its own measurement of polarized dust emission in September 2014, it became clear that the dust in the region of sky that BICEP 2 had observed was brighter than the model BICEP 2 had relied on. The dust was not a trace amount to be subtracted away. It was potentially large enough to account for the entire claimed signal. And then came the joint analysis. In early 2015, the BICEP 2 and Keck Array teams worked together with the Planck collaboration on a combined analysis that used Planck's multi-frequency data on dust, together with BICEP 2 and Keck's higher sensitivity polarization measurements. It was a genuine collaboration between groups that had, until that point, been in something of a competitive relationship. The analysis was careful, it was public, it was peer-reviewed, and its conclusion was, in plain language, that there was no statistically significant evidence for primordial B-mode polarization once the dust was properly accounted for. The signal that BICEP 2 had announced with such confidence in March 2014 was consistent within the uncertainties with polarized dust plus zero cosmological signal. the discovery was gone. Not discredited in the sense of fraud or carelessness. The people involved were serious, skilled scientists working at the frontier of what was technically possible. But a mistake had been made. A foreground had been underestimated, and the estimate had been used with more confidence than the available data supported. And the result of that mistake was one of the most public retractions of a major claimed discovery in modern cosmology. The community felt it. There was embarrassment, certainly, but there was also, in a strange way, something clarifying about what happened next. Because the response was not to give up. The response was to build better instruments that could never make the same mistake again. That is what brings us to where the search stands now. The Keck array replaced and extended BICEP 2's capabilities at the South Pole, observing at multiple frequencies, not one, and gathering data with greater sensitivity. Combined with Planck's frequency coverage, the BICEP and Keck and Planck teams have continued to push the limit. The data set, known as BK18, combining observations from BICEP and Keck through 2018 with Planck's multi-frequency maps, delivered the current best constraint, R less than 0.036, at 95% confidence. That is 5 times more constraining than what BICEP 2's claim implied. And it was achieved without the errors of 2014 because the multi-frequency approach to foreground separation was now built into the methodology from the start. The search continues at the South Pole, and it will continue in the Atacama Desert of Chile, high on a plateau called Llano de Chajnantor, at about 5 kilometers above sea level, where the thin, dry air lets microwave radiation through with minimal absorption. The Simons Observatory is being built there, a collection of small aperture and large aperture telescopes designed specifically for CMB polarization science, with enough frequency coverage to model and subtract foregrounds, and enough raw sensitivity to push the upper limit on R significantly below the current value of 0.036. It is already in the process of coming online, already beginning to gather light from the oldest part of the universe. And beyond the Simons Observatory, the CMB S4 experiment, a proposed collaboration between a large number of American universities and research institutions with telescopes at both the South Pole and the Atacama, envisions the most sensitive ground-based attack on this question that has ever been planned. With enough detectors, enough frequency bands, and enough observing time, CMB S4 would reach sensitivities on R at the level of roughly 0.003, close to the predictions of the Starobinsky model and some other currently surviving plateau potential inflation scenarios. But even the most optimistic ground-based experiment faces a fundamental limitation. You cannot see the whole sky from the ground. The atmosphere, even the thin cold air of the South Pole and the Atacama, absorbs and emits microwaves in ways that limit what you can observe at the largest angular scales, the very scales where the primordial gravitational wave signal would be strongest. From the ground, you see a patch. From space, you see everything, which is why LIGHTBIRD exists. LIGHTBIRD, light satellite for the study of B-mode polarization and inflation from cosmic background radiation detection. The name is almost endearingly literal. It's a Japanese mission, led by the Japan Aerospace Exploration Agency, JAXA, with major contributions from international partners including the European Space Agency and NASA. It was selected as JAXA's second strategic large-class mission, a designation that marks it as a significant long-term national commitment to this science. The design philosophy of LIGHTBIRD is, at its heart, a direct answer to the lesson of 2014. It will observe the full sky from space from the Sun-Earth L2 point, that gravitationally stable position about 1.5 million kilometers from Earth in the direction away from the Sun, the same orbital home that the Planck satellite occupied, the same region where the James Webb Space Telescope now works. From L2, there's no atmosphere to interfere, no ground spillover. No day-night cycle distorting the measurements, just the cold, stable, dark environment that precision microwave observation requires. And light bird will observe at 15 frequency bands, spanning from 34 to 448 gigahertz. 15. Bicep 2 had 1. Light bird has 15, chosen to cover the frequencies where synchrotron radiation dominates, the frequencies where dust dominates, and the frequencies in between where the cosmological signal has its best chance of standing out. With 15 bands, the foreground model is not a guess taken from a conference slide. It is built directly from Lightbird's own measurements of the same sky at the same time with the same instrument, removing the single biggest source of systematic error that undermined Bicep 2. The target sensitivity is delta R less than 0.001 1,000th. If the true value of R is anywhere above 0.01 and if the instrument performs as designed, Lightbird should detect it. If the true value is below 0.001, if the signal is that faint, then Lightbird's non-detection would be a major constraint in itself, strong enough to rule out all but the most subtle inflation models and to put serious pressure on the alternatives. The planned launch is around 2032, carried by a Japanese H-3 rocket. It is worth taking a moment to sit with that date. 2032, 6 or 7 years away, or perhaps a little more by the time you're hearing this. An instrument is being built right now with the explicit purpose of settling the question that has been open since Alan Guth sat down in 1980 and worked out that the universe might have inflated. An instrument designed in the aftermath of a near-Nobel announcement that turned out to be Milky Way dust. A machine built to be, as completely as engineering allows, immune to that mistake. And if it works, if Lightbird launches and observes and the data come back clean, what it might find is this: a faint, unmistakable curl in the polarization of the oldest light in the universe. A twist so gentle that it's invisible to every instrument we've built until now. A pattern spread across the largest scales of the sky, placed there not by any galaxy, not by any dust grain, not by any star or black hole or explosion, but by the violent, microscopic, quantum shuddering of space-time itself in the first 10 to the minus 32 seconds of existence. A ripple from before anything we could call a physical object had formed. A whisper from the epoch when the universe was still, in some sense, deciding what it was going to be. If Lightbird finds it, we will know something extraordinary. We will know not just that inflation happened, we'll know the energy scale at which it happened. The tensor to scalar ratio R encodes that information directly. A larger R means inflation happened at a higher energy scale, a smaller r means it happened at a lower one, and the energy scale where most simple inflation models operate is around 10 to the 16th gigaelectron volts, a trillion times higher than the energy reached by the Large Hadron Collider at CERN. A trillion. We cannot build a particle accelerator that probes that regime. We cannot create those conditions in any laboratory. The early universe is the only place they ever existed, and Lightbird's measurement of R would be the only way we have of reading what happened there. That is not a small thing. That is science reaching into an epoch that is otherwise permanently inaccessible, using the faint fingerprint it left behind on a bath of ancient light. And here is the thing that stays with me, the thing that I keep coming back to as I think about all of this. Whether Lightbird finds the signal or doesn't, the outcome is profound. If it finds a clean B-mode signal, a real R greater than 0.01, then 40 years of inflation theory will have its smoking gun. The framework that began as a solution to the magnetic monopole problem that grew into a comprehensive account of the universe's large-scale structure, that predicted the slight tilt of the spectral index before Planck measured it, that predicted flatness to 0.5% before we had the instruments to confirm it. That framework will have passed its hardest test. the universe's quantum birth cry will have been heard. And we will know as concretely as physics ever knows anything that quantum mechanics and gravity were woven together in that first instant in a way that echoes all the way to us, here, now, 13.8 billion years later. If it finds nothing, if the signal is below 0.001, then the simplest plateau models and the Starobinsky scenario are either very precisely confirmed or in trouble, depending on the exact number. And the alternatives, Steinhardt's cyclic cosmologies, the bouncing models, the ideas that question whether inflation is even the right picture, will gain new traction. Not because they're proven, but because the space where inflation was supposed to live has shrunk to almost nothing, and the question of what really happened at the beginning becomes more open, more strange, more genuinely uncertain than it has been in decades. Either way, we learn something we don't yet know. Either way, the universe's first instant becomes more legible to us than it is tonight. That is an astonishing position to be in. We are not at the end of this story, we are in the long pause before the next chapter, after the false dawn of 2014, and before the result that Lightbird and the Simons Observatory and CMB-S4 might deliver in the years ahead. We are the people who know what question to ask, who have built the instruments to ask it properly this time, and who have not yet heard the answer. And I want you to feel, if you can, what that actually means. You are lying in the dark right now, perhaps in a quiet room, or on a train, or somewhere between sleep and waking. And in some very real sense, the thing we've been circling all night long is not just an abstract puzzle for physicists. It is the story of where you came from and how you got to be here, and why the universe that contains you is the particular shape it is. Because if inflation happened, and all the confirmed evidence we have, the flatness, the spectral tilt, the Gaussianity of the fluctuations, if inflation happened, then the galaxies that eventually formed, including the one our sun was born inside, were seeded by quantum fluctuations. Microscopic, momentary ripples in the inflaton field. Events so small they make an electron look like a continent, and those events were stretched by that violent, almost incomprehensibly brief expansion until they were not microscopic at all but astronomical, until they were spread across the breadth of the universe as gentle density waves, as regions slightly denser and slightly emptier, as the faint blueprint of everything that gravity would eventually build. And gravity did build it. Over hundreds of millions of years, those regions of slightly higher density pulled in surrounding matter. They became clouds of hydrogen, and then the first stars, and then the first galaxies, and then clusters of galaxies, and the great cosmic web of filaments and voids that we can see today when we map the universe at its largest scales. All of it, every galaxy in every image from every telescope that has ever been pointed at the sky, the Milky Way and Andromeda and the Virgo cluster and the Coma cluster and the Sloan Great Wall, and every structure we have names for, and thousands more we don't. All of them are the worked-out consequence of quantum noise that inflation magnified to cosmic scale in the first 10 to the minus 32 seconds. You are, in that sense, made of frozen quantum noise. The carbon in your cells, the iron in your blood, the calcium in your bones, all forged in stars that were born in galaxies that formed along density waves that trace back to a quantum flicker smaller than anything we can directly detect. You are what inflation made possible, not by design, not with any intention, but by the almost incomprehensible chain of cause and consequence that runs from the first instant to here to now, to the particular arrangement of matter that is you, listening. That thought, that the largest things grew from the smallest possible fluctuations, that the universe's structure is quantum mechanics writ enormous, is not a poetic exaggeration. It is the actual prediction of the theory, the thing that makes the search for primordial B-modes more than just an exercise in astronomical precision. It is the thing that gives the hunt its weight, its urgency, its wonder. Because if we can catch the fingerprint of inflation in the twist of ancient light, we are not just confirming a cosmological model, we are tracing the thread all the way back. We are looking at the moment the quantum and the cosmic were the same thing. And somewhere in the sky, in that bath of microwave light that Arno Penzias and Robert Wilson first stumbled on in 1964, thinking the noise might be pigeon droppings in their antenna at Bell Labs, is the answer. It's there, or it isn't. Either inflation printed its signature in the polarization of that ancient light, or it didn't leave a detectable mark. But the light is there. The same light that carried the pattern of hot and cold spots that COBE first glimpsed in 1992, that John Mather and George Smoot built a career toward, that Planck mapped with such precision that the spectral index NES equals 0.965 is now one of the best measured numbers in cosmology. That same light all around us all the time, carrying not just the echoes of the first 380,000 years, but possibly, the echoes of the first 10 to the minus 32 seconds. Think about that for a moment. Let it be a slow thought, the kind you don't need to pin down all at once. The cosmic microwave background is not something far away. It is everywhere. It is all around you right now, filling the room you're in, passing through the walls and through your body, as it has since the universe cooled enough to let light travel freely. When you think of the oldest light in the universe, it might sound like something at the edge of a telescope image, something distant and removed, but it's here. It moves through you. And somewhere inside the pattern of that light, the faintest trace of what happened in the universe's first, unimaginably brief instant may be written in a curl, a handedness, a twist, that we have been trying to read for decades and have not yet succeeded in reading. The dust got in the way in 2014, our own galaxy, the Milky Way, full of its own aligned grains and its own magnetic fields and its own polarized microwave glow, interposed itself between us and the signal we were looking for. That's not a tragedy, it's a reminder that the universe is full of things between us and where we're trying to look, and that patient, systematic, multi-frequency, carefully designed science is the only way through. Lightbird is being built to look through the dust. 15 frequency bands, a full sky view from L2, sensitivity to a signal 36 times fainter than what Bicep 2 thought it had found. It won't launch until around 2032. There will be years of waiting and years of data taking and years of analysis. This is not fast science. It has never been fast science. Alan Guth worked it out in 1980, and we are still in the 2020s hunting the proof. The horizon problem and the flatness problem and the spectral tilt have been addressed. The smoking gun remains elusive. That is fine. That is what the frontier looks like. And here is what I think is beautiful about that. We opened this evening with a question held loosely in front of us like something to carry into sleep. The idea that in the first unimaginably small fraction of a second, the universe wrote a fingerprint. That everything, every galaxy, every star, every arrangement of matter that ever arose or will arise, was shaped in that instant. That the fingerprint is still there, in the oldest light, waiting. And the honest answer, the answer that respects the science and respects you, is that we have found much of the fingerprint already. The flatness is there. The near-scale invariance is there. NES equals 0.965, a number that should not have been what it is if inflation didn't happen. The Gaussianity is there, the adiabaticity is there. These are confirmed, these are done. These are the parts of the fingerprint that Planck and WMAP and the ground-based surveys have already lifted from the ancient light. What remains is the last, hardest part. The part that would tell us the energy scale of inflation, the part that would separate inflation from its rivals, the part that Steinhardt's cyclic alternatives could not produce at detectable levels. That part, the B-mode polarization pattern, the twist in the ancient light, the tensor to scalar ratio R, remains to be found. Maybe it's just below the current limit at R equals 0.02 and Lightbird will catch it cleanly. Maybe it's at 0.05, well within Lightbird's range but invisible to everything before it. Maybe it's below 0.01 and even Lightbird will return an upper limit, and the question will be handed on to an instrument not yet conceived, to physicists not yet born. Maybe, and this is the uncomfortable possibility that Paul Steinhardt and Anna Aegis and others take seriously, the signal doesn't exist at the level that inflation in any of its common forms would produce, and the picture needs to change in ways we haven't fully worked out yet. All of these are live possibilities. All of them are consistent with the evidence we have tonight. And all of them mean the same thing in a certain light. They mean that the universe has not finished telling us its story, that the first instant, that impossible, unwitnessable, quantum mechanical, gravity-shaking first instant, is still sending us information. Not in a mystical sense, but in the most literal, physical sense. The light from that epoch is here. It's passing through the room, and the instruments we're building are learning slowly, patiently, to read it properly. That is an extraordinary thing to fall asleep knowing. Wherever you are right now, whatever time it is in your corner of the night, you are lying in a bath of ancient microwave light that has been traveling toward you since the universe was 380,000 years old, and woven through that light, or perhaps not quite there yet in our ability to find it, or perhaps there at a level just beyond what we can currently measure, is the last unread line of the oldest text in existence. A line written by quantum mechanics and gravity working together in a duration so brief there isn't a word in any human language for how short it was before the first particle, the first atom, the first star, the first anything had formed. The fingerprint of the universe's first instant. We are still hunting it. The telescopes are still turning. The analysis pipelines are still running. The instruments for the next generation are still being built, one careful component at a time, in laboratories in Japan and Europe and the United States, by people who remember 2014 and learned from it and are determined not to be fooled by dust again. And somewhere between now and 2032, or a little after, the data will come in. The frequency bands will be compared, the foreground models will be fitted and subtracted, and what remains will either be something, a faint, unmistakable, beautiful curl in the oldest light, or it will be nothing, and the nothing will itself be a message, a constraint, a door closing on some theories and opening on others. Either way, we will know more than we know tonight. And right now, tonight, I think that is enough. It is enough to know that the question is real and the search is real, and the people doing the searching are serious and careful and have learned from their most public mistake. It is enough to know that the universe left a fingerprint, and that the fingerprint is either waiting to be found or quietly, not quite there, in the form we expected, and that the difference matters enormously and will be known in your lifetime or close to it. It is enough to carry that into sleep. The sense that there is a great question still open, and that it is being asked with the full attention of some of the most careful minds alive, and that the answer is coming. You don't need to hold all of it. The quantum fluctuations, the inflaton field, the 60 E-folds of expansion, the B-mode polarization, the tensor to scalar ratio. Let them go, gently, one at a time, into the quiet. They'll still be there in the morning. The physics doesn't go anywhere while you sleep. The ancient light keeps traveling. What I hope you carry is just this: that the universe began with something small, beyond imagination, and that smallness became everything, and that the everything includes you, and that the signature of that beginning is still moving through you right now, in light too old to name, and that somewhere a satellite is being built to finally read it. That is a good thing to carry into sleep. If you enjoyed this slow drift through the beginning of things, a gentle like or subscribe means more than you might think to a small channel like this one. Small creators like me really do rely on your support to keep these nights going, and I'd love to know, where are you listening from tonight, and what time is it in your corner of the world? Leave it in the comments if you're still awake enough to find them. Until next time, settle in. The ancient light is still here. Good night, kiddo. Grandpa'll leave the porch light on.